axioms. Here's a simple knowledge base. And I've changed this knowledge base very slightly from last Thursday's lecture. We've still got many of the same relations, but we've got a grandparent of relation. So if X is a parent of Y and Y is a parent of Z, then X is a grandparent of Z. And you remember and you read for today about unification. When we want to make an inference, one common form of inference is modus ponens. And so if we have a rule like this, parent implies child, and we have the antecedent for that implication, then we can conclude the consequent of the rule. But in the case of first order predicate calculus, the antecedent or the rule may be bound to constants. It may be very restrictive relative to the generality of the rule itself. And so we have to make sure that the antecedent is really satisfied, and it's satisfied how it's satisfied, and then the implications of that particular way it's satisfied is used to limit the scope of our inference from it. And you remember we talked about unification. We would notice here that parent Mary Jim matches parent of XY. And I'm switching to a convention now that I'll probably use throughout where variables are prefixed by question marks and constants are not. And when I say match, I mean that they will unify. That is, there's some way to substitute. Either there's an exact match because there's only constants involved, or there's a way of binding the variables in one or both of the expressions to constants or variables in the other expression. So in this case, we can unify parent of Mary Jim with parent of XY by binding X to Mary and binding Y to Jim. And at that point, we can apply the substitutions throughout the rule, having done those variable bindings. And so we apply, we substitute Mary for X and Jim for Y throughout the rule. And then we have the bounded rule from which we can apply modus ponens. So we have a specific rule here, which the variables have been bound. We have the antecedent to that implication, and now we can actually conclude the consequent. Because we have the implication, we have the antecedent, and so we can conclude that Jim is a child of Mary. Hopefully that's pretty straightforward. It's a lot like propositional logic, except that we've got to worry about variables and binding those variables to limit the scope of generalization. In the reading you did, we talked a little bit about bottom-up inference, and you can also do top-down inference in the same way that we did with propositional logic. So here's a new rule. If somebody is a grandparent of someone else and that person is a grandparent. So let's say that we want to prove that Mary is a grandparent. We would take the goal that we were trying, in a top-down approach, take the goal that we were trying to prove, grandparent Mary, and we would look for rules. We would either look for an exact match in our knowledge base, and if we don't find an exact match, and we don't, we would look for a rule whose consequent was something that would unify with grandparent Mary. And in this case, it will unify. We can bind X to Mary, and now those two, and then substitute Mary in for X. And those two statements are now identical. We can apply that substitution throughout the rule, and so X is bound to Mary, Y is not bound to anything. From this, if we can demonstrate the truth of this, then we can demonstrate the truth of this through modus ponens. And so we take this now. We've got to demonstrate the truth of this. We look for something in the knowledge base that might unify with that directly. There might be a statement like this, but there are no grandparent of statements. but there is a rule with a consequent or grandparent of xz. So x is bound to Mary in this case, and y is going to be bound to z. The order of substitutions is, when you have two variables like this, is really arbitrary as long as you are consistent in the rule. In this case, this is important because what you'll see happens here is by binding y to z and binding x to Mary, I do that substitution for y. It's important because you'll notice if you look at these various rules that variables named x and y are repeated across these various rules. They're different variables, just like they would be in different functions of a program. They might have the same name, but they're different variables. We've got to make sure that we do the bookkeeping correctly to make sure that an x from this rule is never confused with an x from this rule, or a y from this rule is never confused with a y from this rule. If you were to actually implement a theorem prover in first order logic, this bookkeeping and making sure that you kept these variables distinct, even though they had the same name, would be an important bookkeeping problem. So we apply those substitutions throughout. To demonstrate that Mary is the grandparent of somebody, we have to demonstrate this, which is the antecedents for this rule with the substitutions. We can do this in a few different ways. We can bind Mary to parent, actually that should be parent of. I'll make that correction later. We can bind Mary to, or we can match it to parent of Mary Steve here. And this unifies. So Mary is an exact match, those constants match, and we can bind y to Steve. And then this becomes identical. And then we apply that y value substitution throughout. And so Steve is substituted for y here. And we're still left with a variable, and we would want to show, if we could show that, and parent Mary Steve is actually in the knowledge base, if we could show that parent Steve, somebody bound or unified with something in the knowledge base, then we would have a proof for the original goal. But there is nothing in the knowledge base that unifies with parent Steve. And so I didn't show the substitutions I might have made based on this tentative step here, but because of this failure, this would be a search failure. And we would have to back up, and we would have to undo those variable bindings before trying something else. And that something else is to bind Mary, parent of Mary somebody, with Mary Jim. I can bind that. I can apply the substitutions. In this case, I can unify this with something in the knowledge base. I can unify this by applying, by substituting Jean for Z. And at that point, I've got a ground statement. It's in the knowledge base, and this is sufficient for demonstrating the truth of the original statement. Very often I would go, and during the proof itself, I would keep track of the various substitutions perhaps. And I could return a complete ground proof for what I was trying to demonstrate. What we're going to be doing, just like in propositional logic, and the reason I didn't have you do, or I had you optionally read the material on proofs per se, resolution proofs, was we're going to handle resolution proofs a bit differently than the book, but very much like the way we handled resolution proofs in propositional logic. Here is a statement of axioms. This is from some very old AI book that I have lost track of, but I do remember the example. It's an example about curiosity killing the cat. Jack is an animal lover, so Jack would never kill the cat. A series of simple statements that have been translated into predicate calculus. The couple of interesting things here is, just like propositional, just like our treatment of proofs in propositional logic, we're going to be assuming a particular form for the knowledge base. And that particular form is going to be conjunctive normal form or clause form. So this has been converted into statements that are disjoined, but there's an implicit conjunction, including between these two things. I should put these really on separate lines, but I've put a comma there. There's a conjunction there, implied conjunction across these statements, but disjoined within. There's a couple of transformations that we'll talk about, and everything in this form is, all the variables in this form are universally quantified. So I don't show the quantifications. In this form, there are some variables that are existentially quantified, some variables that are universally quantified. In this form, everything is universally quantified. So how do I translate statements in arbitrary form, axioms in arbitrary form, into clause forms? One thing I have to worry about is getting rid of existentially quantified variables. And there is a strategy that's more complicated than I'm going to show you, but it's essentially replacing existentially quantified variables by constants or by functions more generally. You can think of a constant as a function with 0 parameters. Here, I've taken the existentially quantified variable x, and I've just replaced it with a constant that I've given an arbitrary name to. There is some dog. Give that dog a name. There may be more than one dog, but we don't particularly care. We're just giving, whatever these dogs exist, we are giving them a name. In this case, it is a constant. Now, that oversimplifies just a bit, because I said in general, you might have to replace existentially quantified variables with functions that are more general than this, that actually have parameters. And those parameters would correspond to universally quantified variables in a wider scope. I'm not going to test you on this, on how to translate arbitrary knowledge bases into clause form. I will just assume typically, well, I will assume on the final exam that you can take something that looks like this in clause form, and you can do proofs with it. If you want to practice on doing this translation, it's easy enough, and you can look in several sources or come talk to me about doing it. But just as we did translations from arbitrary knowledge bases in propositional logic, there's going to be some other rules for translation that we're going to be using for predicate logic. One would be rewriting statements like this that are implications in terms of disjunctions. And here, there's an existentially quantified variable, but I'm going to actually get rid of it by virtue of these other transformations that I'm going to do. Just as in propositional logic, if I've got a statement like this, an implication that's equivalent to negating the left-hand side and ORing that with the consequent. So I'm left with this. I can then move a negation inside there exists, and what I get is a for all. So if it is the case that there does not exist variable bindings that will make these true, that is the same as saying for all y, one, this is not true. This conjunction is not true. And I can further move this in, and I get a couple of negated expressions here. And so what I'm left with after this translation is a statement like this. And there are similar statements elsewhere. The same thing, I would do the same thing here. But in any case, this is the final form in clause form. And we're going to be doing, you're going to be responsible for resolution theorem proving with this. Let's say that I want to, and you'll remember in propositional logic, we talked about resolution as well as resolution refutation, which is basically proof by contradiction. So in this particular example, here's my axiom is in clause form. Suppose I want to prove that curiosity killed Tuna, the cat. I would negate that statement, and I would assume it's true in a proof by contradiction. All right, so assuming it's true, and then show that this leads to a contradiction, an explicit contradiction. The way that this would actually work is this would be a search problem. Basically, you would frame this as a search problem, and you would search for a proof. And it could get very complicated, and the state space would be partial proofs that you constructed along the way, and each state would be, you'd expand it in certain ways. On an exam, I'm just going to expect you to be able to do that proof, or do that search rather, for purposes of answering the question. Give a proof for this, and you will do the search. But you can certainly encode this. In past AI classes that I've taught, I've had students build theorem provers for first order predicate calculus, and they've had to use depth first, iterative deepening to do it, for example. So you can frame this as a search problem. But let's just remember the resolution rule and update it a bit for predicate calculus. Here are two statements that we have asserted are true. One is the negation of what we want to prove. This is an assumption. We're proving this is true. And we're inserting this into the axioms and then showing a contradiction. And it, by the way, for this to work out, when you negate this statement and put it into the set of axioms, it needs to be the case that the set of axioms were consistent before the addition of that. Otherwise, if they were inconsistent, if there was already a way to demonstrate a contradiction within a set of axioms or a knowledge base, this method of proof is useless. Any method of proof would be useless in that case. So the assumption is that before adding that negated statement, the set of axioms are consistent. There's no internal contradiction within them. But take a look at these two statements. This is axiom 4, and this is the negated statement. And the assumption is both of these are true. So for both of these to be true, that has to be true. Curiosity did not kill the cat. But over here, part of this disjunction is curiosity killed the cat. And so for those both to be true, it must be the case that Jack killed the cat. Okay? And so when we compute this, what's called a resolvent, we essentially take a look at two different statements, and we look for two different statements in which there is there are two propositions that are identical other than the fact that one is negated and one isn't. And that will lead to the computation of a resolvent, which is the residual of the two statements. In this case, it's just going to be this statement here. We'll see a more complicated example, though. So we're left with this, and we have another statement here in which there's a promise of a contradiction. We've got, this is axiom 3. We've got a not kills statement here. We've got Jack kills Tuna. This will unify with that, with these substitutions. Z is bound to Jack, W is bound to tuna. And then we apply those substitutions throughout this expression. And for both of these to be true, again, for this to be true, because this followed from things that we, axioms that we assumed were true from a correct form of inference, valid form of inference. We apply these throughout. So for this to be true and this statement to be true, it must be the case that one of these is true. And so we can conclude this. And now we're left with this. And again, we would search the set of axioms for the potential for a resolvent. Number 2 gives one potential possibility. This says Jack is not an animal lover. This says X is an animal lover. We can bind X to Jack and then apply those substitutions throughout. And this is the resolvent that we're left with. Now in this case, this phrase and this phrase cancel each other out. And I explained here in a bit of detail, you might need to go back and look at this, but if indeed Jack is an animal lover, then it must be the case that this is false, and so this needs to be true. If Jack is an animal lover, or if Jack is not an animal lover, another problem. If Jack is not an animal lover, then it must be the case that one of these is true. And so a conclusion is take the statements which are not to be resolved out. And this is what we're left with. Just to repeat the strategy that I've been talking about, whenever you get a resolvent and you want to continue looking for a proof, you will look for statements that include the same proposition. Here we have one, a negated animal tuna, and here we have another which are identical, or can be unified rather, into something which is identical, other than one is negated and one isn't. So here, tuna is substituted for you, that's applied throughout, and this is the expression that we are left with at this point. Still no contradiction, but if we continue this proof, this is where we left off. We can unify this with number 5, cat tuna. And in this case, the substitution list is empty because there's only constants involved in what we're unifying out, and we're left with this expression. This will unify with 1b, that Jack owns the dog, and if you unify 1b with this statement, you're simply left with D is not a dog. And here you get an explicit contradiction because we have an axiom that says D is a dog. Typically, you could leave the proof as D is a dog and D is not a dog as an explicit contradiction. It's usually the way it's handled in an implementation is you would resolve those two and you would be left with null. And if you're left with null, then you've demonstrated an explicit contradiction. This is called a set of support proof strategy, because every expression here, or every resolution step, involves either something which is negated as part of the negated statement of what we want to prove, or it's some descendant of that. So from the very first step, we use the negated statement, and every step after that, we used a descendant of that negated statement as one of the resolvents in the proof. Here's another refutation proof. I'm not sure you can read it, but the slides will be posted later. You can go back and look at it. But this is not set of support. It's still a valid proof, but at each step, it does not necessarily use the negated statement or its descendants. The reason that a set of support strategy is intuitively nice is if, in fact, you are introducing, this negation is introducing what amounts to the contradiction, then it intuitively, it is probably, in most cases, going to lead to a more efficient proof, shorter number of steps to find the contradiction than a non-set of support strategy. So prove this statement, S of A, by a resolution refutation proof. These are the axioms in clause form. Why don't you take a couple minutes and see if you can do that. Can anyone read slide 25? Anyone's eyes that good? Mine used to be. I used to have 2013 vision, but I can promise you no more. It's long gone.
I would guess the projector is the limiting factor, not the eyes.
Really? Yeah. How many people think that they've got it? They just haven't written it out, but they sort of see where the next few steps are. Okay, that's good enough. I don't want to have too much of a delay in the video, but you know, the first thing you're going to do is you're going to negate this, and you're going to assume it's true, the negation of this. So you would have not SA, and that is what introduces A into this problem in general. I mean, to begin with. Without adding that negated statement, A wouldn't be part of the steps. This is not set of support. We don't use the negation of SA in every step or its descendants. But you can go through this. Here's PW, QW, not QY here, S. We can unify these two. They are the same proposition other than variables when is negated, but we unify that, substitute Y for W throughout, and with the appropriate substitutions, these residual expressions are left as a result. We can conclude this. At some point, we are left with S of Z here. We can unify as unnegated. We can unify that with S of A, and with that binding, we're left with null. So take a look at that proof later. If you were to do this without, use resolution without refutation, it would look something of the same, but again, without resolution, without refutation, you'd be still doing resolution steps here. At some point, you'd be left with an expression like this, and then you'd simply substitute A in for Z using a non-resolution step, universal instantiation, to do that substitution. You might wonder why resolution with refutation is preferred possibly to resolution without refutation. It's because resolution with refutation or proof by contradiction is complete. It is all you need. You don't need any other inference operators if you are using refutation resolution. And intuitively, we're not going to go into depth about that, but intuitively is that negating the statement you want to prove and inserting it to the set of axioms allows you to show some things that you could not show by resolution alone without adding that negation. So we talked about unification here. There was a quiz on unification. Hopefully it was clear after you got the answers. But here's an exercise in unification. I could see asking this on the final exam, but show the result of unifying these two expressions. What you want to do is you want to unify this expression with this one and then apply the substitutions. There are various, you'll see various implementations of unification, but intuitively you're not going to have to, you're going to have to simply perform unification, and you could use any of a number of algorithms for doing that. But in this case, if you want to unify this expression and this expression, and then substitute throughout, including the Q expression, because that's what you're going to be left with after resolving those two, is you would go through argument by argument. You would first make sure that the proposition or predicate names were the same. You'd look at the first argument. You would bind y to z, or vice versa. As long as you're consistent, it will work out. And so you would substitute all instances, you would substitute z for all instances of y, and you would do that over here in the Q expression too. You would go to the next one. You would substitute z for x. X would be bound to z. Again, you'd apply those substitutions throughout. You'd be doing a couple more. You'd be getting this point. In this case, you've got a constant and a variable. In this case, you would bind w to b, and you would apply that substitution throughout. There are no instances of w over here. And finally, you would get to this comparison of this last argument, and you would bind z to a, and then you would apply that substitution throughout your expression, throughout all the expressions, including the Q expression. And so the final answer of what you'd be left with if you were to resolve those two expressions would be this one. Yeah.